Hi everybody. This lesson is concerned with various types of probability distribution. We start by examining various important univariate discrete distributions, such as the binomial distribution and the Poisson distribution. We then introduce various univariate continuous distributions, such as the exponential, normal, and gamma distributions. After that, we will discuss multivariate distributions, i.e. distributions involving two or more random variables, and we will end by introducing conditional distributions, which allow us to answer questions about the probability of one random variable x, given that we know something about the value of another random variable y. Here we also formally introduce the notion of independence of random variables. This is a notion which we have already used in an informal sense when dealing with samples drawn from some distribution. So let's begin by considering some important univariate discrete distributions. The Bernoulli P distribution is a distribution with one parameter, P, which is a probability, and corresponds to the distribution of a random variable x, which takes two possible values, namely 1 and 0, where the probability that x takes the value 1 is P, and therefore the probability that x takes the value 0 is 1 minus P. For example, this can be associated with a coin flip where the probability of obtaining a heads is P. A related distribution is the binomial distribution with parameters n and p. Here n is a positive integer, a natural number, and p is a probability, in other words a number between 0 and 1. And this corresponds to a random variable x, such that the probability that x takes the value k is equal to n combination k times p to the k times 1 minus p to the n minus k for all the values k from 0 up to n. In other words, the possible values of x in this case are the values in this set 0, 1 up to n. This distribution is used to count the number of successes in n independent trials, given that the probability of success per trial is p. As an example, consider a coin with a probability p of landing h and fix a natural number n. Let x be the number of heads after n tosses. Then x has the binomial NP distribution. To see this, let's consider an example. Suppose that we toss a coin n is equal to 5 times, and that the probability of getting a heads, i.e. a success, is 0.4. Let x be the number of heads. And let's compute the probability that x is equal to k, where k is equal to 3. Now the probability of getting a particular outcome where x is equal to 3, for example the outcome heads, heads, tails, tails, heads, is p times 1 minus p times 1 minus p times p in this case. And that's p to the k, p cubed, times 1 minus p to the n minus k, 1 minus p squared. And since p is equal to 0.4, we can compute this as 0.02304. Now here we have 5 places. We've got heads in the first place, heads in the second place, tails in the third place, etc. And so we have 5 places. And these must be filled with heads and tails. And for x to be equal to 3, it's required that we fill this with 3 heads and 2 tails. That means we must select 3 out of the 5 places to put the heads. We can do that in 5 combination 3 ways, in other words, in n combination k ways. And in this case, that's equal to 10. Now, each such outcome has a probability of p to the k times 1 minus p to the n minus k. And since there are n combination k outcomes, we see that the probability that x is equal to k is exactly this expression here. Since n combination k is equal to 10 in this case, that amounts to 0.2304. In other words, 10 times this quantity here. Observe that the Bernoulli P distribution is just the binomial 1p distribution. In other words, it corresponds to one coin toss. Furthermore, note that if x1 up to xn are independent Bernoulli P random variables, then their sum is binomial NP. In essence, each of these x's takes the value 0 or 1, corresponding to a failure or a success, and so the sum is the number of ones and therefore equal to the number of successes. Let's have a look at the probability mass function of the binomial distribution. Here we take the parameters n is equal to 10 and p is equal to 0.5. In other words, it corresponds to 10 coin tosses, each with a probability of 0.5 of landing heads. In that case, the probability mass function looks like this. Since the probability of landing heads is 0.5, we expect 5 out of the 10 to be heads, and so, as you can see, we have a maximum at 5. We can change this. For example, if I make the probability of success very small, then I expect it to be quite likely that there are hardly any successes, in which case the probability is skewed very much to the left. The probability of getting 0 successes is about 0.35, the probability of getting 1 success is about 0.4, etc. Let's go back to this case where the probability is 0.5, and let's have a look at the CDF of this random variable. The CDF can be obtained from the PDF simply by having a jump equal to the size of the PDF at that point at each of those points. So, for example, the height of the mass function here is precisely equal to the jump size here. Of course, the y-axes are not on the same scale, so it doesn't look like they are the same. Another important discrete distribution is the Poisson-Lambda distribution. It has a single parameter, lambda, which is any strictly positive real number, and corresponds to a random variable x, which can take values 0, 1, 2, 3, etc., and where the probability that x is equal to k is equal to e to the minus lambda times lambda to the k over k factorial. This distribution is used to count rare events which occur independently of each other. If certain events, for example defaults or insurance claims, arrive randomly at a rate of lambda per unit time, and x is the number of events after 1 unit time, then x has the Poisson-Lambda distribution. To see this, note that the Poisson-Lambda distribution is a limit of the binomial NP distribution, where n goes to infinity and p goes to 0 in such a way that n times p is equal to lambda stays constant. In other words, we keep the expected number of arrivals constant at lambda. Assume that events arrive independently at a rate of lambda per unit time. Take the unit interval from 0 to 1 and divide that into a large number n of subintervals, where n is so large that the probability of more than one event per subinterval is negligible. In other words, each subinterval has either 0 or 1 event in it. The probability of observing a single event in a given subinterval is then lambda over n, because each subinterval has length 1 over n. If we regard an event occurring in a subinterval as a success, then the probability of seeing k events in unit time is equivalent to seeing k successes, and that probability is given by the binomial distribution as shown here. Now, a little bit of manipulation shows that this quantity on the left here is equal to this quantity here. Now we keep k fixed and we let n go to infinity. It's well known that as n goes to infinity, this quantity over here goes to e to the minus lambda. On the other hand, a little thought shows that as n goes to infinity, but k stays fixed, both this term here and this term here go to 1. And thus, if we keep k fixed and let n go to infinity, then the probability of seeing k events per unit time is just lambda to the k over k factorial times e to the minus lambda, which is exactly the Poisson distribution. Let's have a look at the Poisson distribution with parameter lambda is equal to 2. Here is the probability mass function. We expect 2 events per unit time, so the probability of seeing either 0, 1, 2 or 3 is reasonably high, but then it drops off, and the probability of seeing 6 or more events per unit time is negligible. If we increase lambda, for example, suppose we make lambda is equal to 5, then we have a higher probability of seeing 5 events per unit time. The bigger lambda is, the more this probability gets skewed towards the right. I've shown here the probabilities from 0 up to 20, but this continues up to infinity, unlike the binomial distribution, which is 0 from n onwards, where n is the parameter, the first parameter of the binomial distribution. So for example, if I make this equal to 15, it will be heavily skewed to the right, and now we need to extend the x-axis to actually see what's going on there. So if I extend it to say 40, we get the following. The CDF, again, is just a step function with a jump at each of the mass points, in other words, at each integer.